Are there any questions over the homework? Remember, we've skipped 4.2, so we've done 4.1 and we've started 4.3.
Is this 4.2 still on the list?
No.
Oh,
It got taken down.
oh, it's good.
I got you.
All right. The last example we looked at was the x e to the negative x. Did anyone have any questions about our conclusion?
So we have to remember the domains of like all these different graphs.
Yeah. So you need to know the domains, otherwise you can't technically correctly classify what's a critical point and what's not a critical point. Okay. So we've seen a few examples of testing where a function is increasing and decreasing. The next theorem gives us really a 2-for-1 when you come up with this sign chart for f prime of x, because not only will we be able to determine from the sign chart with the pluses and the minus from the first derivative where the function is increasing and decreasing, but it also tells us where the function has maximums and minimums, meaning the local maximums and local minimums. So if you can think about what would actually define a maximum or a minimum on a function, what would that be? Other than a high point or a low point. Like, think about what really happens when you have a maximum or a minimum on a function. Can anybody just give me an idea of what actually has to happen to have a local max or a local min?
Change of direction.
Change of direction? What do you mean direction?
Like of the line. So like
So, something like that,
if
for
it's
instance.
going up, it'll go down.
Okay, so if it's going up, then it'll go down, right?
Yeah.
So like this would be our maximum. If we just looked at it like by points, our points would do something like this. And then we would have this point here, and then this one, and then this one, and so forth. So that would be our local max. So changing directions, going up and then going down.
Gosh, I just had it in my head. When it goes from positive to negative or negative to positive, like the slope.
The slope, right. So when the slope goes from positive to negative, meaning when the function goes from increasing to decreasing. So our function here is increasing up to that point, and then after that point it starts to decrease, right? So that classifies that as a local maximum. A similar situation here, our function is decreasing to this point, and then after this point it starts to increase again. So the change in the function from increasing to decreasing or decreasing to increasing classifies a local maximum or a local minimum. And again, to determine the intervals of increase-decrease, we're looking at the sign chart for the first derivative. So when the first derivative changes signs from positive to negative or from negative to positive, you have a local minimum or a local maximum depending on what the sign change is. So that's what's discussed here in this theorem called the first derivative test. And really it's in addition to what we were doing in those last two examples. So the first derivative test says if f prime changes from positive to negative as x increases through c, then f has a local maximum. So, an example of that would be, here's the sign chart for our first derivative, here's some critical point, and the first derivative is changing from positive to negative. But again, what we know or should remember about the original function is that this chart tells us that f of x here at this critical point is increasing up to that point, and then it decreases. So, a more exaggerated version of that, you're looking at something that increases and then decreases. We have this peak here at this value, which, that's corresponding to that critical point. So that's actually how we tell whether or not a critical point is corresponding to a local minimum or a maximum, right? Because critical points were only candidates for local minimums or local maximums. Similarly, if the first derivative changes signs from negative to positive, then we have a local minimum at that critical point. So again, if we're looking at the chart for first derivative, and the first derivative is negative and then positive, that means the function is decreasing and then it's increasing, so you have a local minimum here. Whatever that critical point was. So really, you get quite a bit of information just from the sign chart on the first derivative. Not only do you get intervals of increasing and decreasing, but you also get any local minimums or local maximums. And then the third situation is if it's positive or negative on both sides, then there is no local min or local max. So that's why not all critical points correspond to a local extreme. If we found this to be a critical point of the first derivative, and let's say the derivative is positive and then positive again, that critical point doesn't correspond to a local minimum or a local maximum. Let me go back and label this item 3 here. Does anyone have any questions on that theorem? Does that make sense? Need clarification? Okay, so we'll look at this example then. State the intervals of increasing and decreasing like the first two examples, and now we can also identify any local extreme. So there is there's one or two homework questions where you do have to deal with negative exponents. So once we get there, we'll mention what to do when you're dealing with negative exponents. So the intervals of increasing and decreasing and local extrema are defined in terms of the first derivative. So when you see these problems, you need to find the first derivative and then find the critical points of the first derivative. So what's the derivative of f? Power rules. We have 2/3 times 2, x to the 2/3 minus 1, or minus 3/3. So 4/3 x to the negative 1/3 minus 5/3 x to the 2/3. So when we're moving forward with finding the critical points where the first derivative is 0, where the first derivative is undefined, this is kind of where looking at exponents that are positive and negative in two different ways are beneficial. So for like solving this equation equal to 0, I think it's more beneficial to leave it as it is with the exponents just as they are. And then when we look at where it's undefined, maybe to rewrite the negative exponents. Okay, so we'll look at where the first derivative is 0 and where the first derivative is undefined. So let's maybe start with where the first derivative is undefined. Where is the first derivative not defined? For what values of x?
Zero.
X equals to 0. What do y'all think? Because the negative exponent is contributing to that. That's really 4/3. And then we have x to the negative 1/3, which is really, x to the 1/3 down here. So that's 4/3 cube root of x on the bottom, minus 5 cube root of x squared over 3 on top. Okay, so that's equivalently our first derivative. When it's written out like that, then it's clear to see that x can't be 0 from this one right here. Okay. So we would say our first derivative is undefined at x equals to 0. Now, before we actually classify x equals to 0 as a critical point, what do we need to make sure of? Where do critical points have to be?
Within the domain.
Within the domain of f of x. So we didn't find the domain yet. So at some point, you're going to need to go back and look at the domain of the original function. Whether we did it initially or whether we're doing it now, trying to classify critical points, it really doesn't make a difference, but at some point you'll have to do so. What is the domain of this function? Yeah, all real numbers. We just have even roots involved. Or sorry, odd roots. So when we say our first derivative is undefined when x is equal to 0, that is an acceptable critical point. Do you have any questions at this point? Okay, so solving now the first derivative equal to 0, it's more beneficial to leave it in the form we have it currently. So 90% of the 95% of the time, maybe 99% of the time, it's really just a matter of taking out the greatest common factor. So what's our greatest common factor here? Certainly 1/3. What power of x? So you probably, more than likely, haven't done a whole lot of, factoring out powers of x that involve positive and negative exponents. The trick is when you see something like that is you take out the smallest negative. Usually the greatest common factor, we say we'll take the largest power that all of them have in common. But with these kinds of positive and negative exponents mixed, we just want to look for the smallest negative one and take that out. So we will just factor out the x to the negative 1/3. If you factored out x to the 2/3, then you would still have negative exponents left over. So we don't want those, we have one, but it's sort of isolated. So factor out the lowest negative exponent that all terms have. And then what are we left over with? Or what's left over here? I'll do the first one. It's 4 minus 5. There's going to be a power on x with the 5 though, because we just factored out the negative 1/3 from the 2/3. So what power of x is here? So maybe if you think about it, reversing the process, if I distribute the 1/3 x to the negative 1/3 back to the 4, I'm back up to this term. If I distribute it here to the 5 to this, or negative 5x to some power, I should get 5/3 x to the 2/3. Well, so what do we do when we multiply this x to this power times this x to that power? What do we do with their powers? You add them together, right? So, what we're actually looking at is, if I take this negative 1/3 and add that to this power that I'm trying to figure out, what should I get? I should get back this 2/3. So then you've got a simple algebraic equation to solve for question mark.
So 3/3, which is 1.
Yeah, so it's 3/3, which is 1. So that's just 5x to the first. Okay. And so now we have two things multiplying to give us 0. We can set those individual things equal to 0 and solve. So our first derivative is 0. We'll just write this, f prime of x equals 0 when 1/3 x to the negative 1/3 is 0. And when the 4 minus 5x is 0. So this one probably a little more straightforward here. When x is 4/5. Is that a critical point? When the first derivative is 0 and it's on the interior of the function's domain. So here's one critical point. That was the other one. And when is 1/3 x to the negative 1/3 equal to 0? Doesn't exist. There is no value of x to make that 0. Again, this is 1/3 times the cube root of x. So when does a fraction equal 0? When the numerator is 0, the numerator is always 1. So this never equals to 0. So we only have two critical points coming out of this, 4/5 and 0. Any questions at this point? So now is the time where we test values in the first derivative determined by our critical point. So we're taking our first derivative on its domain. we had a critical point here at 4/5 and a critical point here at 0. As a reminder, we're going to rewrite our first derivative here. Unless you're using a calculator to test values, the case where we have the derivative factored, it's always easier to check the sign in the factored version than it is, the full-on expanded version of the derivative. Okay, so what values do we want to test in the first derivative?
-1.
Okay, so we'll choose -1 over here. 3/5.
One's easier.
Well, what is 4/5?
One on the other side.
Yeah, so the 4/5 is smaller than 1, so we can test 1 on that side.
You can do 1/5.
They do 1/5 over here. Okay, so we're evaluating f prime of those three values, -1, f prime of 1/5, and f prime of 1. So, let's see what we get. So when x is -1, what do we get in the first derivative? It's what? What is this factor?
9.
Yeah, so that factor is positive. It's 4 plus 5. So that factor is positive. Is this factor positive or negative?
Negative.
-1 to the -1/3 is, remember, that's -1 on the bottom, cube root of -1. -1 times 1/3 is negative. So we have a negative times a positive, which is a negative. Again, we don't care about the number itself, we just want to know the sign, because all we're after is where the first derivative is positive and negative. So over here, it's negative. F prime of 1/5, does anyone have that yet? So if I take the cube root of 1/5 is positive times 1/3 is positive. 4 minus 5 over 5, 4 minus 1 is positive. So this is positive. And then f prime of 1. Yes, first factor, 1/3 times the cube root of 1, positive, and then 4 minus 5 is negative. Positive times negative.
Will we ever need the numbers for anything?
No. And so again, that's much easier. If we had the graph of what f prime looked like, it would be super easy to tell when is it above the x-axis and when is it below. But we don't want to graph this just to determine those signs. So it might seem tedious, but it's a whole lot less tedious than graphing the first derivative. Okay. Questions on any of this? Yeah?
Are those referring to slope or just above and below the x-axis?
Just above and below.
Okay.
Yeah, so that's just to be taken literally as it is. It's only when we use that chart to tell us information about the original function, that's when we'll talk about its slope being positive or negative. In other words, the function is increasing or it's decreasing.
Okay.
All right. Any other questions about what we're doing? We also look at the second derivative with pretty much the exact same procedure that we're applying here. It tells us additional information about the function, but it's crucial that we're all on the same page with this process because it's identical to the second derivatives procedure. All right, so we did all of that work to get this chart, and then we're going to let this chart tell us what's happening on the original function. If the first derivative is negative, the original function f of x is decreasing. First derivative is positive, f of x is increasing and decreasing. I mean, you don't necessarily have to write or draw out the table or the number line here for the original function. I just taking that extra step just so we can see what the implication is. Okay, and then what else do we know? If the function, if f of x is decreasing and then it increases, what happens here at this point?
Your local minimum.
Local minimum? Yeah, so we're decreasing, then it's increasing, and then it decreases again. So here at this point, local maximum. So we get intervals of increasing, decreasing, and local maximum, local minimum. Is everybody cool with that? Does that make sense? Are there questions or comments?
That's at 0 and 4/5.
Yep.
Okay.
Yep, so that's occurring at those critical points that we found in the first derivative. Again, that diagram there that we've written here in black is not necessary. It's just the conclusion and what the sign chart for the first derivative is telling us is the necessary component. So we want to sum this up by saying f of x is increasing on the interval 0 to 4/5. Decreasing on whatever those intervals were, 0, negative infinity, sorry, to 0, and 4/5 to infinity. And f of x has a local minimum at x equals to 0. That was our critical point here when the function went from decreasing to increasing at x equals to 0. a value of the local minimum.
X equals 0.
Yeah, whose value is the original function evaluated at x. 0. In other words, the local minimum occurs at the origins, the point 0, 0. And a local maximum at x equal to 4/5. And the value is f evaluated at 4/5. It's about 1.034. So we want to write all of that out as our final result in some clear way. Don't just leave the sign chart for the first derivative. Do y'all have any questions on that? All right, let's look at the actual graph. All right, so there's our local minimum at when x is 0, whose value is f of 0, which was 0. And then local maximum when x was 4/5, whose value is 1.034. Also recall that when we found the first derivative, we said the first derivative was undefined when x equals to 0. Looking at the graph, we see why the first derivative is undefined. Does anybody remember the cases where the first derivative is undefined? At vertical asymptotes.
I get corners.
So yeah, at corners, and the more gradual corners still followed. I said vertical asymptote. I meant horizontal or vertical tangent line rather. So when the tangent line becomes horizontal, when the tangent line becomes vertical at these more gradual corners, which they call cusps. So this is a more gradual corner, right? It doesn't just have a sharp edge like the absolute value does. You know, we just see that gradually getting more and more vertical as we get to the origin. So our work here that supported that was this part right here. The first derivative is undefined when x is equal to 0, because this graph has a cusp, which is a vertical tangent there. Any questions on that? Okay, the next theorem tells us that if you have one local extreme, either a minimum or a maximum, but not both, just one local extreme, then that's the absolute extreme. So if you've got one local minimum and only one local minimum, nothing else, then you know that's an absolute minimum. If you have one local maximum and no other maximums or mins, then you know that's also the absolute maximum. And I think, you know, a really straightforward way to remember that is just to remember something like f of x equals to x squared. Where if we looked at the function on its domain, we would come up with the fact that it has a local minimum here, and no other extremes, no other minimums, no other maximums. So knowing that it's the only local minimum tells us by this theorem that it's also the absolute minimum. Remember, we can't guarantee both absolute minimum and absolute maximum on x squared because it's not defined on a closed interval. It is continuous, but we didn't define it on a closed interval. Or negative x squared would be the example of where one local maximum implies the absolute maximum. And we'll also use that here for this example to show f of x equals x to the x has an absolute extreme on its domain. So does anybody remember the domain for that? We talked about it when we were in the logarithmic differentiation section. What's the alternative way to write x to the x? And it involved properties or inverse properties of natural log and e.
E to the power of x ln x?
Right, yeah. Yep. Okay, so does that help us remember the domain?
0 to positive infinity.
Yeah, 0 to infinity. Because of the logarithm, sorry, natural logarithm. Okay, so we want to show that function has an absolute extreme on its domain, which is from 0 to infinity. With functions like that, we had two options to take the derivative. We could say x to the x is e to the x ln of x, and then just use the chain rule on e to this power. Or we could use logarithmic differentiation with x to the x. So do you all have a preference? Okay, logarithmic differentiation. So we'll stick with this function here. So we're going to find f prime of x using logarithmic differentiation. Okay, so, or if you want to just leave f of x, that's fine. But we're going to take the natural log of both sides. And simplify the right-hand side of the equation with, or using properties of logarithms. So at this point, it kind of builds into the fact that we can rewrite that as e to the x ln of x, right? We're gonna take the derivative from this point, but what if I exponentiated both sides? What's e to the ln of y? Is equal to y. That's just y here. And then this is just e to the x ln of x. Y equals e to the x ln of x. So we, I guess, can see that in another way if necessary. Okay, so now, once we've taken the log, simplified, we're going to take the derivative of both sides. So we're differentiating that. What's the derivative of the natural log of y?
Y over Y prime.
It's close.
Y prime over Y.
Yeah, y prime over y. This is f prime over f, or y prime over y. What's the derivative of x times the natural log of x?
It's a
Part of it.
product rule.
Yeah, it's a product rule. So we have x times the derivative of the natural log of x, so that's x over x, first derivative of the second, plus the second times the derivative of the first. And then we're going to multiply through by y. We did this example in chapter 3, so I'm not going to spend a whole lot of time on it. Y was x to the x, so we have x to the x times 1 plus ln of x as the derivative. So find the derivative, then we find the critical points of the derivative. So when does our derivative equal 0? It's already factored for us. We know it's 0 when either one of those factors is 0. So when does x to the x equal 0? Yeah, how do you know that?
Plug in 0.
Well, yeah, in that sense, we got to be careful, and we don't see that until 4.7. But 0 to the 0, in the sense of a limit, is what they call an indeterminate form, which means that it can have any value. So sometimes 0 to the 0 in that sense is 5, sometimes it's negative 12, sometimes it's 100. But if we can recall that x to the x is the same thing as e to the x ln x, when does that 0? When is that equal to 0?
It's never.
Yeah, so that's easier to see, right? The exponential is never 0. Okay, no critical point from there. When does 1 plus ln of x equal 0?
Need to go first?
Super close.
Or can you subtract negative first?
Yeah, so that's the same as when ln of x is negative 1, and then we just exponentiate both sides. E to the ln of x is x equals to e to the negative 1. Or 1 over e. I don't know if I actually did 1 over e. Compute that. Is that in the domain of the original function? The domain of the original function x to the x was 0 to infinity. Certainly in the domain. So we have critical point here. And then we want to know, is the first derivative ever undefined on its domain? Okay, there's our first derivative. So we already know the domain of x to the x is 0 to infinity. What's the domain of 1 plus ln of x? One's fine. What's the domain of ln of x? 0 to infinity, right? So this is, the domain of this function is just 0 to infinity. Is this domain here is 0 to infinity, and this one is the same. So you don't add any other restrictions from the natural log function. So yeah, the first derivative is undefined at 0 and all negative values, right? But we wouldn't call 0 and all negative values critical points because all of those values aren't in the domain of the original function, which again just happens to be the domain of the derivative as well.
So when you say that x is undefined at 0?
I mean, you could say it's undefined at 0, but we wouldn't classify that as a critical point because 0 isn't in the domain of the original function. So how do I want to say this? We'll just say that it's not undefined. The first derivative is defined on the domain of the original function, so there's no exclusions that we have to make here. So we only walk away with the one critical point at 1 over e. So we're going to look at the derivative, which was defined from 0 to infinity, and our critical point was at e to the negative 1. So what two values do we want to choose to test in the first derivative? Okay, 0.2 and 0.4. Let's do. So just need one value needs to be smaller than e to the negative 1, and one value needs to be larger. And choose whatever values you want. And maybe we're thinking alternatively this way. So let's evaluate f prime at e to the negative 2. So x to the x or e to the x ln of x, is that Is that always negative, 0, positive? What is it? It's exponential. It's always positive. Right? E to any power. Don't think about the x ln of x, because that's just going to give you some number. Whether that number x ln of x comes out to be positive or negative or 0, e to that power is always positive. So that factor x to the x, or e to the x ln of x, is always positive. And we just need to figure out what's e to the negative 2 plugged in here. 1 plus ln of e to the negative 2 would give me what? What's ln of e to the negative 2? Negative 2. So this is negative 2 plus 1, which is negative. So you've got a positive times a negative, which is a negative. So its first derivative is negative there. How about the first derivative evaluated at e?
Is it positive?
Positive. Again, e to the x ln of x, that factor is always positive. And then we have 1 plus ln of e, which is 1, so that's just 1 plus 1. Just want to plug it into your calculator, that's fine too. Sorry, I'm right, this is positive times positive. So first derivative is positive over here. Then what do we know about the function x to the x?
Decreases and then increases.
Yeah, so it's decreasing from 0 to 1 over e, and then it increases from 1 over e to infinity. What else do we know? There's a local minimum, because the function f is decreasing and then it increases. So you've got a couple of things here. So f of x is decreasing from 0 to 1 over e, or e to the negative 1. Increasing from 1 over e to infinity. And has a local minimum at x equal to 1 over e. And so if we looked at the chart for f, if you want to reference that, the chart for f, we have 1 over e. The function is decreasing, and then it increases. So there's our local minimum. Primarily, though, we're going to go back to the to this. Where was that? We're going back to theorem 4.9, which says that if your function has only one local extreme, then that's also an absolute extreme. So what we've done here is shown that x to the x, it only has this one local extreme, which means that's also the absolute extreme. So also by that theorem, since f of x has only local min, it would work the same way if there was only one local max. Is everyone clear on that? So it only has that local minimum at x equal to 1 over e. This is also the absolute minimum. Okay, so there's the function x to the x. There's the only local minimum, which is also the absolute lowest, absolute minimum. Do you have any questions on that example? Notice this this point here is actually it's not an actual point. It's actually a hole here. So remember, the domain of this function was from 0, not including 0, to infinity. So we know from the domain that that function can't include x equals to 0. But how do we know that that location is a hole? And how do we know that y-coordinate of that hole is also at 1? So the idea of answering something like that on a graph such as this is what we address, part of what we address in 4.7. So to find this hole here, we would have to look at what's the limit as x approaches 0 from the right on the function x to the x. We see from the graph that it's 1, but we don't actually look at this process until 4.7. Any questions at all? So now we're going to take what we've been doing with the first derivative, apply that to the second derivative, and that's going to give us additional information about the function f of x. And that information is the concavity and inflection points. So the definition of concavity, notice how it's defined. It says that if the first derivative, if f prime is increasing, it's concave up. So concavity is described in terms of the first derivative. The first derivative is increasing, or where the first derivative is decreasing, you have the function itself, f of x, is concave down. So there's just a diagram to show that. I often think of, like, when you look at a graph, it's most of the time it's really easy to tell where the maximums and minimums are, and where the function changes from increasing to decreasing. That's pretty straightforward. However, when you look at a graph, most of the time it's not clear where the concavity changes. So like this is concave up and then it's concave down, but where does it start from going, stop being concave up and start being concave down? Like, where does that transition point occur? That transition point is called the inflection point. So the function changes concavity at a certain location. That C value is your inflection point. So notice the analogy here is where the second derivative changes sign, we get an inflection point, whereas the first derivative, when it changes signs, you get a local minimum or a local maximum. Okay, so how will we decide where the first derivative is increasing? Because where the first derivative is increasing, the function is concave up. Similarly, how do we decide where the first derivative is decreasing, so we can determine where the function is concave down? So to answer the question about concavity, that we have to, by definition, answer the question, where is the first derivative increasing and decreasing? How do we do that? So thinking back to what we just did, where is a given function f of x increasing or decreasing? How do we determine that?
Create the table.
Yeah, we created the table on the, for the first derivative, yeah. So where is this function increasing or decreasing? We look at the first derivative. So where is the first derivative increasing or decreasing? We have to look at what?
The second derivative?
The second derivative, yeah. Where is the function increasing or decreasing? We had to look at the first derivative. Where is the first derivative increasing, decreasing? You have to look at the second derivative. Where is the fifth derivative increasing and decreasing? You have to look at the sixth derivative. Yeah, so that pattern is consistent all the way through. All right, erase that. And maybe just in general, we can say here, to determine where any function is increasing or decreasing. Whether the function is some derivative or not, we just look at first derivative, or we could say more generally, the subsequent derivative. Again, in order to, if I wanted to know where the 10th derivative was increasing and decreasing, then I would look at its 11th derivative. Specifically, that means, like we said, for us to determine where f prime is increasing and decreasing. Again, going back up to the definition, when f prime is increasing, what does that mean about the original function? When f prime is increasing. If f prime is increasing, then f is concave up. So what we're saying is, how do we decide where f prime is increasing or decreasing? What we could equivalently say is, where is f of x concave up, concave down? That is an equivalent question. So we're just going to look at the sign chart. For the second derivative. So here's a kind of a generic example. I'm going to start with my second derivative, and let's just say we have just this one 0 right here. I don't know, at x equal to 0. So the second derivative is 0 when x is 0. Let's just say that. And we've tested this. On the left, we know that the second derivative is positive, and on the right, the second derivative is negative. All right, so if we were given that, or if we know that information, what do we know about the first derivative?
Increasing and decreasing.
Right, so this positive here tells us that the first, on the second derivative, tells us the first derivative is increasing, and the negative on the second derivative tells us the first derivative is decreasing. So I can just erase one of these primes here, and then I'm looking at f of x and looking at f prime, right? So it's telling us the same information, we're just adding an additional derivative. And another step further, by definition, where the first derivative is increasing, the original function is, I'm just going to abbreviate that, concave up. And where the first derivative is decreasing, the function is concave down. So since there's layers to that, there's two different ways to think about concavity. The original function is concave down when the first derivative is decreasing. Or the original function is concave down when the second derivative is negative. Same thing with concave up. And so in practice, when you're asked what are the intervals for which the function is increasing and decreasing, and where are the intervals which is concave up and down, we'll just separate them out. Intervals of increasing and decreasing, we'll just look at the first derivative like we did for all those other examples, and then we'll look at the second derivative to tell us about the concavity. But it is important to recognize that this sort of nesting feature of our derivatives does occur like all the way through, as long as you have a differentiable function up to n derivatives. So again, like just a more to illustrate that, like if this were the fifth derivative, then this information tells us something about the fourth derivative, and then again that tells us information about the third derivative. The same sort of information we could have stacked all the way through. Does that make sense? Okay. So we'll look at, we've got one example we'll look at, and then honestly, once we get to the next section, it's graphing functions using all of the graphing techniques that you know, right? Like the x and the y intercepts, the horizontal, vertical asymptotes, all of that kind of stuff, with the addition of intervals of increasing, decreasing, and concavity. So we basically take this section 4.3 and put it on top of all of the other information you know about graphing, and then we get a more accurate graph. And that's really what 4.4 is. Do y'all have any questions before we go on break?
Yeah.
Did everyone get a handout? Okay. So the first side, how derivatives affect the shape of the graph, is just some, I guess, general information on the procedures that we're working through. And perhaps the back you won't reference, but it's, if you're given the graph of a function and or the graph of a derivative, how do you draw the respective function? Like, how would you draw the first derivative? How would you draw the original function? It's kind of just a chart on a column by column basis. Use that if you want. If you have any questions about it, also feel free to ask. So with the second derivative stuff, the comparison to the first derivative stuff is pretty much dead on. And if you remember when we looked at the first derivative and found the critical points, just because you had a critical point didn't necessarily mean you would have a local minimum or a local maximum. And also, just because you have a critical point didn't mean that there was going to be a change, or in other words, a change in sign from positive to negative or negative to positive. The same criteria, I suppose, is true for the second derivative. So just make a note of both of those. Well, and then the other one was where we could also have, like in that example with our fractional exponents, where the first derivative was undefined, you could have a local minimum or a local maximum. So the analogy to the second derivative is concavity and inflection points. So just as when the first derivative is equals to 0 or undefined, does not imply, the function has a local minimum or a local maximum. The same is true for the second derivative. When the second derivative is 0 or undefined, that does not imply the original function will have an inflection point. And just for reference, an example, for example, the function x to the fourth, the second derivative is 0 when x is 0, but the graph of x to the fourth doesn't change concavity at 0. So that would be, there wouldn't be an inflection point there if the second derivative didn't change signs. The second thing we want to keep in mind, just like with the first derivative, when the second derivative is undefined, f of x, the original function, can have an inflection point. I'm just going to abbreviate that, IP, inflection point. So an example of that would be when f of x is x to the third, 1/3 rather, or the cube root of x. So the second derivative of that function is undefined, but there is an inflection point. And so that's true if we can remember the stuff with the first derivative as far as local minimums or maximums concerned. So the first derivative can have a local minimum or maximum when it's undefined. And just because you have a critical point of the first derivative doesn't necessarily mean there's a local minimum or maximum. Same idea extends to the second derivative, is with the point of that. All right, do y'all have any questions? So we'll look at one example. State the intervals of concavity and identify any inflection points for the inverse sine of x on the interval from -1 to 1, not including the endpoints. Does anyone remember the domain for inverse sine? No. We had to restrict the domain of sine to get it to be 1 to 1. So the domain for inverse sine was -1 to 1, but included the endpoints. Like we saw another example of a question like this where they said do this on the following interval. So when that occurs, that is now effectively your domain, regardless of the domain of the original function. So that more or less you're given a new domain for this function to work with. Okay, so to find the intervals of concavity and inflection points, we're just going to look at the second derivative sign chart. Where the second derivative is positive, your function is concave up, and where the second derivative is negative, your function is concave down. Also, where we change signs on the second derivative indicates inflection points. So first derivative for inverse sine, anybody remember that? Oh, super close.
1 minus x squared.
Yeah, 1 over root 1 minus x squared. So at this stage, we're not worried about the first derivative sign chart. If we wanted to know the intervals of increasing and decreasing, local mins and local max, then that's when we would start, well, where's the first derivative 0 and undefined, test across those values. But since we're specifically only looking for intervals of concavity, we're just using the first derivative to get to the second derivative. Okay, so I guess you could look at this as a quotient, or you could rewrite this as 1 minus x squared to the -1/2 and use the chain rule. So which one do we want to do? Chain rule or quotient? Chain chain rule. So the second derivative is -1/2, 1 minus x squared. We're subtracting 1 from that power, so minus 3/2 power, multiplied by the derivative of the inside. So this, of course, is minus 2x. So what we have is we're going to combine the minus 2x with the -1/2 to give us just x. So there's our second derivative. Writing it with positive exponents, we have x over the square root of 1 minus x squared to the third. Oops. Can we simplify that any further? Or will we just leave it?
Leave it?
I'll just leave it. Second derivative. So it really doesn't matter which one we work with. What we want to do now is figure out where the second derivative is 0 and where the second derivative is undefined. Just terminology-wise, we don't call where the second derivative is 0 and undefined, we don't call those critical points. Critical points are solely reserved for the first derivative. It's escaping me if they are labeled as such. Maybe they're called like hyperpoints or something, I don't know. But critical points reserved for the first derivative. But it's the same procedure. We figure out where the second derivative is 0. So where's the second derivative 0? When's a fraction 0? The denominator is 0, the fraction is undefined. When the numerator is 0. So this one's second derivative is 0 when x is 0. Is that in the domain? Yeah, the domain was from -1 to 1. So we have that one. Where is the second derivative undefined? And x is what?
1.
1. Anywhere else?
-1.
-1 as well. Are those things we're going to consider? Oops. What's the domain of the function?
1 to -1.
-1 to 1. Are we going to include those? No, because it has to be on the inside of the domain. Oh, that's not. That's terrible. So not on the interior. Of the domain. So we're not including these. So our second derivative has one value we're testing around. Same as the first derivative. We're going to draw the domain out for the second derivative from -1 to 1. And then we're going to test on either side of this value here. So maybe we choose, I don't know, 1/2 and -1/2. Evaluate the second derivative at those two test points. So there was our second derivative at 1/2 and -1/2. So what would f double prime rather of -1/2 give us?
Still just be positive. Right now, negative, that's
So we can let's just plug that in. We use the either version, doesn't matter. And then that's cubed. Positive or negative? Okay, so you have 1 minus 1/4, positive number, cubed, or square root rather, is still positive, cube a positive number, still positive, negative over a positive, so negative. And f double prime at 1/2, what would that give us? Positive, because you've got a positive over a positive. Remember this, the square root always produces output of a positive number. Cubing a positive number is always positive. Okay, so there's our sign chart for the second derivative. Okay, so then what do we conclude about f of x? Based off of this chart here.
It's decreasing and then increasing.
That would be true if this were the first derivative. We would say that the function is decreasing and increasing.
So it'd be concave up.
Yeah, so here is concave up from 0 to 1, and then concave down from -1 to 0. We could also say that since we've got the sign chart for the second derivative, the first derivative from -1 to 0 is decreasing, and the first derivative from 0 to 1 is increasing. But second derivative, as far as the original function concerned, will tell us concavity. So we'll say f of x is concave up on the interval 0 to 1. And again, just be mindful of the domain of the function, because if we were to just to draw out the number line, you might have written down the wrong answer and said it's concave up from 0 to infinity, which isn't true. So it's concave up here, concave down from -1 to 0. And the sign chart also tells us what? when we change from positive, when concavity changes from concave up to concave down or vice versa. Inflection point. So it's the second derivative would tell us inflection point. No, if that were the first derivative, a local minimum would occur there. Inflection point. So since the function changes concavity across 0, there's also an inflection point. At that x value, x equals to 0. Now, it's a point of inflection, so we want to describe it as an ordered pair in most cases. And we're talking about the original function, so that x value needs to go back into the original function to determine the point on the original function where concavity changes. So an inflection point at 0, 0 with those intervals of concavity. Does anyone have any questions on that example or the process? So like I said, looking at the graph, it isn't totally clear where the concavity is up or down and where that concavity changes. So this, going through this explicitly shows us that the function here is concave down. And here, concave up. I think visually, an easy way to differentiate between concavity being up or down, concave, something that's concave up, if it were part of a vessel, would hold liquid. So, you know, if this were part of a cup or something like this, you know, and we're just imagining it's over here as well, then that part would hold liquid. Assuming everything's like oriented in the same way, right? Like we're gonna pour liquid into the cup sitting on the table. So I don't know if that's a helpful way to think of it, but at least visually, maybe it can help. It's not always clear, like I said, just looking at a graph where it's concave up. Okay, and then of course our inflection point here. Questions at all? Yeah.
When we put the second derivative equal to 0, is that always going to be the inflection point?
Not always. So when the second derivative is equal to 0 or undefined, that will not always be your inflection point. So just like the first derivative, your critical point of the first derivative didn't always correspond to a local minimum or a local maximum. It's the same idea translated to the second derivative. I think the example that we gave in that instance was x to the 4th. So if we just looked at the graph of x to the 4th, the second derivative would be 0 here. But again, when we look at the chart for the second derivative, it's positive on both sides of it. So this entire graph of x to the 4th is just concave up. Yeah, any other questions? Yeah.
So if you get that, do do you put there's no inflection point, or?
Yeah, you would just say there's none, no inflection points, yeah, that's fine.
Okay.
And then the interval of concavity here is just from negative infinity to positive infinity. Any other questions? Okay. One more thing to mention, although not, I don't know, I wouldn't say that, but we're going to mention this. As far as the exam's concerned, I'm not going to test you directly on this. I will say, though, that this theorem, if we're not going to utilize it in practice on the exam, is a good candidate for like a fill in the blank or a short answer. We'll just at least discuss what it says, but it's another way to test for local minimums and local maximums. In practice, I don't think it's utilized that often because we already have a test for local minimums and local maximums. We just use the first derivative. The advantage of that test is it's always conclusive. Either you have one or you don't. This test, notice that last bullet, if a certain condition happens, the test is inconclusive. So it does have disadvantages in that sense. But what it says is the second derivative is continuous on an interval containing C, with the first derivative evaluated at C equal to 0. So C is a critical point. And then it says if we take that critical point, x equals to c, plug that into our second derivative. If the second derivative is positive at the critical point, then you've got a local minimum. The second derivative is negative at a critical point, then you've got a local maximum. So instead of looking at, like a sign chart of the first derivative like this, and saying, well, the function is increasing and decreasing, I have a maximum. This is just another way to look for a local maximum or local minimum. If it does come out to be identical to 0, then it's inconclusive, which means you've got to go back to the first derivative test to determine if it is a local max or a minimum. So we'll note that here. If this is the case, you've got to go back to the first derivative test. But a lot of times in these problems, you're finding intervals of increasing, decreasing, and concavity. So you're in many of these problems, you have the first and the second derivative already. So you could take this route if you wanted to. And maybe just to kind of rationalize this a little bit, if the first derivative at a certain value, or sorry, the second derivative at a particular value is positive, what does that mean about the function itself? Like if I know the second derivative is positive, the function itself is what? We just did that. Yeah, concave up. So this says, another way to look at this is if the function f is concave up about this point, and we've got a critical point there at c, then there's a local minimum. So we're saying here the function, I don't know, let's draw it out. Like this is c. So that's when your first derivative is 0. That's where the function is horizontal. It's flat there. But we know about this point the function is concave up because the second derivative is positive. And the tangent line, the first derivative is 0 here. So that's telling us we have a local minimum. The second bullet, if the second derivative is negative around, or at C, then the function's concave down. So I mean, it could just be concave down like that, but the other condition where the first derivative is 0 at C gives us that we have to have a local maximum there. So maybe to make some visual sense of what that theorem is saying, you can look at that. But again, this is not often utilized in practice, just because of that third bullet. Do you all have any questions about that? All right, then we'll take all of this information and throw it into our bin of graphing techniques. And then that's virtually what we're doing in section 4.4. So graphing functions, the new stuff is just what we talked about, the intervals of increasing decrease, max and mins, concavity and inflection points. And so with like the other points like x-intercepts, asymptotes, behavior near asymptotes, like all of that stuff, in addition to, we're gonna kind of stitch the function together with one of 4 types of pieces. So the first derivative will tell us increasing or decreasing, and then the second derivative will tell us the concavity. So when we put those together to get a clearer picture of the original function, there's 4 outcomes. On an interval, the function can be increasing in concave up, increasing concave down, or decreasing concave up, decreasing concave down. So depending on what interval corresponds to which one, we'll get a piece of that function that looks something similar to those pieces we have there. So like x to the 4th, if we go through the graphing procedures, we would get the fact that it's from negative infinity to 0, that it's decreasing and concave up. So from here to 0, we have decreasing and concave up. And then after 0, we would have the information that it's increasing and concave up. So then we would have this piece stitched here with this piece to give us that shape. And it's a little better than what we have without this information, but you know, I guess the disadvantage is, you know, determining how drastic this is actually curved. So just do your best. This will be similar to an exam question as far as graphing, because there is if you follow the guidelines in the textbook, there is a lot of things they want you to find. And so these problems are very lengthy if we're going through this by hand. So on the exam, if I say graph this function, state the intervals of increasing, decreasing, local min, max, concavity, etc. I'll give you the function and I'll give you the first and second derivatives. That way you don't have to spend time finding that. Because, you know, as you know, with these quotients, sometimes it's pretty tedious to compute the derivatives. So we're given f of x and the first and second derivative. And we're only going to look at this example. It's pretty time consuming. Your homework consists of polynomials, a couple of rational functions like this, and one trig function that you have to graph using the techniques in 4.4. So since the rational functions have weird things happening like asymptotes, I chose to do one of those as opposed to like a polynomial or a trig function. As far as the guidelines and what I want to see from this on the exam, I'll have that stated. So the first thing we want to state is the domain. So what's the domain of our function? F of x?
X can't equal 1 or -1.
Yeah, -1 and 1. So we're excluding -1 and 1. And then we've got to think about what other information do we know about these types of functions. I know how to find the x-intercept and the y-intercept, or sorry, the x-intercepts, if there are any, and the y-intercept. I hopefully should know or be able to determine if there's any holes, vertical asymptotes, and horizontal asymptotes. So what are the vertical asymptotes or asymptotes of this function?
For which one? Which one are we looking at? The original?
Yeah, f of x. Remember, the first and second derivatives are only used for intervals of increasing, decreasing, and concavity.
So wouldn't it be -1 and 1?
Yeah. So there aren't any holes, no factors cancel out. So our vertical asymptotes are at x equal -1 and at x equal to 1. No holes or no removable discontinuities. How about the horizontal asymptote?
Or equal 0?
Yeah. If you forgot the criteria as far as like the algebraic way to determine horizontal asymptotes, calculus approach is to do what? How do we find a horizontal asymptote?
At infinity.
Limit at infinity, right? So y equals to 0 is our horizontal asymptote. So for rational functions, you just need to look at leading term over leading term. So 3x over x squared simplifies to 3 over x, which approaches 0. Other things we can find, x, the x-intercepts. What would the x-intercepts for the function 3x over x squared minus 1 be?
You just set the top to 0, so wouldn't it be 0?
Right. So the x-intercept is just when the function's 0. The function's 0 when the numerator 3x is 0. That is x-intercept is 0, 0. How about the y-intercept?
When x equals 0.
Yeah, so x, we're just going to plug in x equal to 0 into that function, which gives us 0. Fortunately, we didn't get a whole lot of information from those 2 points. Honestly, with these graphs, it's like rational functions. You've looked at techniques in algebra and pre-calc to graph those fairly accurately. The techniques that we're adding with increase, decrease, concavity, that's really not going to add too much detail to the graph. I mean, we're getting a lot more information as far as like mathematically what's happening on the graph, but visually, it doesn't really give us that much more help. So with that in mind, we still want to go through all of these processes on the exam just to indicate that we know how to do that stuff, okay? So don't just, graph this in an algebraic fashion and expect full credit. All right, then that's pretty much all of the old stuff applied to rational functions. Now we'll look at the new stuff with the first and second derivative test. So we had, let's mark this here, intervals of increasing and decreasing, and any local extreme. For those, we're using the first derivative given to us as -3 times x squared plus 1 all over x squared minus 1 squared. Okay, so first derivative is undefined and the first derivative is 0. We gotta find those values. So when is that 0? Fraction 0 when? What happens?
When the top is 0.
When the numerator is 0, is the numerator 0 for values of x? Numerator is 0 when x squared plus 1 is 0, when x squared is -1. Is that ever 0? Not for any real numbers. When is the second derivative undefined? I'm sorry, first derivative undefined, my bad.
1 and -1.
Yeah, when the denominator is 0, at x equals to 1 and -1, are those critical points? No, how come?
They're not in the domain.
They're not in the domain. So we don't have critical points. How do we then construct the first derivative chart? So there's nothing, initially from this we would think, well, there's nothing to like mark on there to test left and right of. But remember the whole point of these tests with the first and second derivatives is to tell us information about the original function. So often on these rational functions this does occur. We just have to remember on the original function itself, here at -1 there's a vertical asymptote. And at +1, there's a vertical asymptote. So that's giving us sort of this implicit information. If the function itself is partitioned into those 3 different regions, then when we look at the first derivative test, it has to be partitioned that way as well. So not explicitly are we given critical points, but implicitly we are given, from the domain of the function, we do know that we have kind of compartmentalized in this way. So we'll choose a value like 0, 2 and -2 to test into the first derivative. And so for time purposes, we'll just go ahead and draw this out. This is, all three of them are negative. So we evaluate the first derivative at -2, 0, and +2. The first derivative is negative. And maybe you can see that from the first derivative itself. The x squared plus 1 quantities and x squared minus 1 squared, those two things are always positive, no matter what you plug in for x. So the first derivative is always negative because of that -3 right there. So what does this chart tell us about the function?
It's always decreasing.
Yeah, it's decreasing on its domain. So when we say f of x is decreasing on what interval? You don't sound very sure about that. So we'll say negative infinity to positive. What do y'all think?
Isn't it excluding -1?
Right, yeah, so you gotta be careful, even though it's decreasing in that chart, the domain of the function is split up, right? Because we can't pass through 1 and we can't pass through -1. So you don't wanna say negative infinity to positive infinity. You wanna say negative infinity to -1, -1 to 1, and 1 to infinity. It's accurate to say that the function is always decreasing on its domain, but the domain isn't all real numbers. There's the domain. Are there any local minimums or maximums? No. No, we don't change sign. Even if we did change signs, like maybe this were negative and then positive, would we say that there's a local minimum or maximum at x equal to -1? No, because the function doesn't include that. We know there's an asymptote there. Nothing happens there. You can't have a minimum or a maximum at an asymptote. Okay, so that's pretty much all of the information that we've got from the first derivative test. And we'll do the same thing with the second derivative. Removals of concavity and inflection points with the second derivative. Same procedure. When is the second derivative 0?
We're still not done?
No.
0, x equals 0.
When the top is 0 when x equals to 0. So x squared plus 3 is never 0. When's the second derivative undefined? Is x squared minus 1 to the third 0? That 1 and -1? Do we include those as part of our test? No, again, they're not in the domain of the function. We just get this x equals to 0 to test in the second derivative, or around. So again, the important thing here is that the second derivative is also telling us information about the first. So when we draw the chart for the second derivative, we want to make sure that that's accurately representing, the function here asymptote at -1 and a vertical asymptote at +1. But now we're coming up with this value of 0 in the second derivative. So really now we have to test 4 things. To test at -2, -1/2, +1/2, and +2. So that's a time-saving thing here, but it's negative, then it's positive, then second derivative is negative, and then positive. So that's going to tell us our intervals of concavity and if we have any inflection points. And then once we have the first and second derivative, we're going to put those two pieces of information together so we can form these shapes and get an idea of what the actual function looks like. So we'll start there on Tuesday. See ya. Down?
Yeah.
So the last one we were doing?
Yeah.
Then go. I gotta play diplomacy first. Then go. To be honest, I watched a video on Facebook about that exactly. No game, and they go back to the League of Legends or Warcraft. Yeah. Like, I want to branch this. And then they try to like, nah, I like this. I don't want to do it on diplomacy. Blood and thunder. You know, blood and thunder from everything.